In this video we are going to talk about the moment of inertia of some fundamental 0 to 2-dimensional objects like for example a point, a rod, a rectangle, a ring and a disk. Okay, if you're looking for 3-dimensional objects, then I recommend you another video that I have made, and I will link to it in the video description. There we will be covering something like spheres or cylinders. Okay, so let's remember the moment of inertia, or the definition of the moment of inertia. So moment of inertia equals the sum of all mi r perpendicular I squared. This is basically the mass of a tiny part of an object times the corresponding radius or the corresponding distance of that object towards a certain axis that the object is spinning around. Okay, so if we have our object here, this is just a point mass, then this point mass is spinning around this axis here, and the corresponding Ri perpendicular is in this case big R, capital R's here, and yeah, that's all the same for every object. And an equally valid definition is that I equals the integral of over the whole mass over R perpendicular squared dm of R, and that equals the integral of over the whole volume of R perpendicular squared times the mass density of R times dV. This is the most general form of this moment of inertia. But in this video we will only be covering the objects with a constant density, so the mass will be equally distributed along the object, or each point will have the same mass. Okay, and in this case we can just write it like this. So this is the integral over the mass m over R perpendicular squared dm, and since dm is actually rho times dv, so the density times a volume, essentially, we can just pull out this density and write it in front of the integral, because that will be a constant. Okay, next thing is the parallel axis theorem, and this will also be good to know if you're calculating moments of inertia. And it basically says that if we know the moment of inertia of an object that's rotating around the axis that's going through the center of mass of this object, then we also know the moment of inertia for this object towards a parallel axis. And if we know the distance to that axis, and we know the mass of the object, and we know the moment of inertia of this object that's rotating around an axis that goes through the center of mass, then we also know the moment of inertia corresponding to an axis that is parallel to the axis through the center of mass. Okay, so let's just go ahead and calculate the moment of inertia for a point. And here we can use this very simple definition up here, and we just sum over all masses and over all corresponding distances to the axis. And this is just going to be I equals, and the only mass that contributes to this center to this moment of inertia is just m, and the corresponding R value is capital R. We square that, and that's it for the point. Okay, let's go to the uniform rod. Uniform thin rod. Uniform means that the mass is going to be equally distributed along this rod, and thin means that it's going to have one dimension. It's not going to have 3 dimensions. It's not going to have a width or a height or a radius. Okay, this rod only has a length L. So we are going to calculate it now as follows. We just say I equals the integral over r squared dm, and I'm not always going to write r perpendicular. Little r is just always r perpendicular in this case. Okay, the integral over r squared dm. And what is dm? Well, dm, it's going to have a linear density, so dm is rho times dv, right? And rho in this case is not mass per cubic meter or something. It's going to have a mass per length because it's only one-dimensional object. So we're going to write it like that. It's mass per length, and dv is also just going to be dr, right? It's just going to be one tiny piece of this of the length of this rod, and we call this the radius, the current radius, basically. Okay, so now we write the m over l in front of the integral because these are constants, over the integral of times the integral of r squared dr, and we just evaluate this from we evaluate it from minus L over 2 to L over 2, because if we imagine this axis here, then this point corresponds to minus L over 2, and that point corresponds to L over 2. L over 2. There we go. Okay, we integrate from minus L over 2 to L over 2, and that's going to be m over L times L to the power of 3 over 8 minus it's going to be 1/3, I forgot 1/3, plus, so plus L over 2 over 8, and that's going to be 2/3 m over L times L cubed over 8, and that's just 1/4 times 1/3 equals 1 over 12 times m times L squared. Okay, there we go. And now we are just going to calculate it for the rod that, and it's rotating around one of its ends. It's rotating not around its center, but one of its ends. Okay, and we are going to, for that we're going to use the parallel axis theorem, because we are just shifting the axis to the left, basically, here. And the parallel axis theorem says that's going to be the center, the moment of inertia through the center of mass plus d squared times m. D squared, d is obviously going to be L over 2 because we're shifting the coordinate system like L over 2 to the left, and m is going to be just m, capital M in our case, and I0, moment of inertia 0, is 1 over 12 ml squared. So let's go ahead and do that. This is equal to 1 over 12 ml squared. Oh, I just forgot it. I'm sorry. Plus d squared times m. Okay. D squared is L squared over 4 times m. And that's m times L squared times 1/12 plus 1/4 is 3 over 12, and we got 4 over 12. 4 over 12. And this is equal to 1/3 ml squared. And there we go, you've just calculated that. We were already finished. Okay, this was one dimension, and now let's proceed to 2 dimensions. We have here a rectangle that is uniform, mass is distributed equally across all of this area here, and it's rotating around its z-axis here. So z-axis, imagine that coming out of the screen. Okay, and it has a height and it has a certain width, and just for better, better understanding, I just drew an x-axis and a y-axis here. So we have some kind of, we can just orient ourselves on these two axes. Okay, let's go ahead and calculate it. That is just going to be the integral of r squared dm. And r squared is going to be r perpendicular squared. I'm just going to write it here because I wrote it in this drawing. And r perpendicular squared, well, what is this exactly? This is going to be basically x squared plus y squared. And if we take r perpendicular squared is x squared plus y squared, because that's just basic Pythagorean theorem here. And therefore we just write x squared, or this is going to be over the whole mass, this is going to be over the area, x squared plus y squared. And what do we have? dA. And dA is obviously going to be dx times dy, because if we're taking such a tiny thing a tiny rectangle out of this rectangle, the area of this will be dx times dy. And since we have dx and dy, we also need to have two different integrals. Let's first integrate over dy. So from dy we integrate from minus h over 2 to h over 2. So minus h over 2 to h over 2, and dy. And now we're going to integrate from for dx, we're going to integrate from minus w over 2 to w over 2, minus w over 2. Okay, and this is going to be dx, and we're integrating over x squared plus y squared. Okay, so this is just, you just calculate this integral here, and whatever pops out of this calculation you just plug in into this integral here. So basically you could also write this dy at the other side. Just wouldn't make a difference, but I'm just going to leave it here because it's, from my perspective, it's a little bit more. You can see that you first have to evaluate this thing on the right side, and then you proceed with the left side. Don't want to mingle it all together. It just doesn't look very good. Okay, so this is just basic algebra and calculating a little bit, and this is just going to be, I'm just going to give you the result right away. 1 over 12 times times w squared plus h squared. Okay, I would just leave it to you to figure that out yourself. I'm just too lazy right now. Sorry for that. Okay, next thing is a ring. This is a thin ring, so it's not going to have a width or something, and it will have a constant radius r perpendicular. And since it's going to have a constant radius, we can just say I equals. So for each point, the radius is equal. That is r over the whole mass, r squared over the whole mass dm. And yeah, since r perpendicular is constant, r perpendicular squared is also going to be constant. So we just write r perpendicular squared times integral over dm, and integral over dm over the mass is obviously going to be just m. And if we call r perpendicular squared just capital R for the radius, and we call this m, then this is going to be our solution for this. Okay, that was pretty simple, right? Now it's going to be a little bit more difficult. Okay, we have a disk here, and this disk is going to be uniform and thin. It's not going to have a height or something. It's not going to be a cylinder. It's just a flat disk that it's rotating, and it's rotating around the z-axis or z-axis. Sorry, I'm not a native speaker, but however, we'll just continue calculating it. So I equals the integral from over the whole mass, let's say, r perpendicular squared dm. And in our case, you know, we are building this up from we're building the surface area up of these tiny of these rings. You know, we have first a little very small ring, then we add a little bigger ring, and these rings are getting bigger and bigger and bigger, and up to the point that it's just going to have the radius capital R here. And we're adding the surface area of all those rings, and then we're left with the surface area of the whole thing, and we need that to calculate the moment of inertia, right? So this is going to be, dm is going to be the density, right? Rho times dv, but in this case it's not going to be volume, it's going to be a surface area, let's say dA, and rho is going to be not a linear mass distribution, but it's going to be mass density. Sorry, it's going to be a mass density, a mass spread out across a surface. So the whole surface of this thing is obviously going to be pi r squared, if you remember that, and the mass is just going to be m. So divided by pi r squared. And then we multiply that by dA, and dA of such a ring is going to be just the circumference of this ring. So circumference of this ring is 2 pi times little r for a specific r. And yeah, then it's also going to have the width dr. So dr. Okay. If you just imagine like some ring here. Oh, I'm sorry. I'm so bad. Okay, this is this ring, and it's going to have a radius or a width of dr. The width is going to be dr, and circumference is going to be 2 pi r, and we just multiply it by that, and then we are going to have the surface area of this ring. Okay. Luckily, I have some tools up here, you know, that help me out drawing circles and stuff. I'm going to use it in the future. Okay, so we just write this pi r squared times 2 pi r, or 2 pi, sorry, this r belongs into the integral over r, basically to the r cubed, because we are going to have this r perpendicular is basically the same thing like this r, so these are basically equal. Or I could also write r perpendicular here, so it's just a little bit more clear. R perpendicular cubed, or just going to write, you know, r for all those things. dr, of course, because we have dr here, and this equals, if we cancel out that pi here, we have 2m over r squared times 1/4, and we are integrating from 0 to r, basically, to big R, and this is just going to be capital R to the power of 4. And then we can cancel out capital R to the power of 2, and we're left with 2 divided by 4. Now this is just going to be 1/2 times m times r to the power of 2. Okay, there we go. I hope you understood some things here, and you know, those things with the differentials are not always that clear. So I just want to make a video because on YouTube there weren't really much information on this. Okay, thanks for watching, and maybe we will see us in another video.